This is Richard Walker from Lucidate. Welcome to this second video in a series of 5 focusing on the Ethereum blockchain. In the first video, we introduced Ethereum. We explored why Ethereum exists, described how the key elements work, and discussed what type of applications can run on it. In this video, we're going to take a closer look at Solidity, the programming language of Ethereum. In the next 2 videos, we're going to build a couple of things using Solidity. We'll build our own cryptocurrency, and after that, we'll develop our own non-fungible tokens, NFTs, and deploy them to the OpenSea exchange. In the final video in this series, we'll look at further practical applications of Solidity and Ethereum and ask ourselves, what's next? In order to best analyze Solidity, we will do the following things. Firstly, we will look at a reasonably complex example of a smart contract, that of an up and in barrier option. We won't dive into the details here, but we will use this conceptually to set the scene for some of the more detailed material that follows. Ethereum and Solidity are designed to provide simpler and more cost-effective services to more people. The human capital intensive nature of capital markets means that its benefits are enjoyed by only a small number of large firms, serviced by a small number of large banks. Replacing human capital with Solidity code means that analogous but less complex products can be deployed to bring the benefits of capital markets to a larger number of smaller firms. Ethereum and Solidity are not seeking to be general purpose technology. They're not designed to develop medical imaging systems, AI solutions for driverless cars, or scientific applications for subatomic particle research. The laser focus of Ethereum and Solidity is financial applications on a decentralized blockchain network. As such, there are some specific things that you can build into the Solidity language to support financial transactions. These include accounts. As we shall see in the knock-in option example, we need to support payments of funds from one account to another. We also need to fund contracts with currency, such as paying option premium. Furthermore, we need to withdraw funds from contracts, such as the receipt of currency from a derivatives contract. And also, funds may need to be transferred between contracts themselves. We'll look at the rich account structures built into Solidity to support all of these use cases. Built-in objects. Knowing that we're building financial applications built on a blockchain means that Solidity can provide some upfront built-in objects and methods to specifically support rapid deployment of applications. Users won't want to have to develop their own objects for interacting with the blockchain, nor should they seek to write their own code for transactions or accounts. By providing built-in objects for frequently occurring interactions, Solidity not only makes app deployment simpler, but it also provides standardized ways for handling transaction messages or interaction with the blockchain. We'll take a look at some of the built-in objects and functions of Solidity later in this video. Security. Permissioning, access control, and security are paramount in any financial application. With Ethereum, this is even more crucial, as all information exists on a public, decentralized ledger. Making it simple to implement security and access control is a vital feature of Solidity. As you would expect, there are many elements of security functionality built into Solidity. Two of the most important are function modifiers and the require statement. We'll take a closer look at these towards the end of this video. So to kick off, let's pick a smart contract example. We'll look at an up and in barrier option. Recall that a European call option gives the option holder a right to buy an asset at a specific price on a future date. The specific price is called the strike price of the option. The option holder pays the option writer premium in return for this right to buy at the strike price. If on exercise of the option, the underlying asset is above the strike price, then the option is said to be in the money. The option holder can purchase the asset from the option writer and then sell it in the open market at a higher price. If the asset price is below the strike price, then the option is out of the money and expires worthless. The option writer keeps the premium in both cases. A knock-in barrier option has an additional feature, the barrier. The option will not knock in until the price reaches this barrier. Even if the asset is above the strike price upon expiration, the option will expire worthless if the barrier has not been triggered. Barrier options typically have lower premiums than vanilla options to account for the fact that the barrier increases the chances that the option will expire worthless. We can illustrate how this process from option writing through to settlement can all be handled with smart contracts on an Ethereum blockchain. An initial smart contract would contain the details of the barrier option, the strike, the barrier, the premium, etc., as well as all the account details of the holder and the writer. If the barrier is triggered, then this smart contract would invoke other smart contracts. One might be to handle payments of additional premium, rebates, or financing costs. Another would be the call option that has been knocked in. All of this would happen automatically on the distributed ledger. Once the contracts are written, they are immutable and cannot be changed. The entire Ethereum blockchain can be visualized as a distributed supercomputer with interaction between loosely coupled smart contracts. No central party is in control. Users have the option to make use of as much of the existing functionality as they wish, or write their own smart contracts to contribute to the overall network functionality. As each contract is added, the capability of the whole network is enhanced. The code is the legal contract, and the legal contract is the code. Entire enterprise applications can be built by composing existing smart contracts. Let's talk about accounts. Accounts are a fundamental element of Solidity. They come in two types: externally owned accounts and contract accounts. Both types of accounts share attributes in common. They have an address where they live on the blockchain and from where they can be invoked. They have a public key so that funds can be sent to them, and they contain balances of Ether or some other cryptocurrency. Externally owned accounts are controlled by a private key, and they cost nothing to create. Contract accounts, however, have no private key. They're controlled by their contract code. As deploying them makes a material change to the Ethereum blockchain, there is a gas cost to deploy a contract account. A fundamental property of a financial system, perhaps the fundamental property, is the transfer of assets. Assets in Ethereum can be Ether, the native currency of the Ethereum blockchain, or any currency that you devise. In the next video, we'll show how to create, deploy, and mint your own cryptocurrency. As we mentioned earlier in this video, there are some distinct use cases for asset transfer. These include simple payments, which in Ethereum are transfers between externally owned accounts, or they can be more complex, such as funding a contract, withdrawing funds from a contract, or transfer of funds from one contract to another. The various modes of asset transfer are shown on your screen. All of these use cases are supported natively and simply on the Ethereum blockchain. The concept of native support then extends to some of the most useful objects and features of the Solidity language. Recall that Solidity doesn't seek to be a general purpose language. Instead, it's laser focused on supporting DeFi apps on the Ethereum blockchain. With that in mind, the developers of Solidity provided some incredibly useful objects as part of the language. These objects and their functions can be accessed directly from within any smart contract. There are two great reasons to do this. First, no one has to write code to interact with the blockchain, to interact with messages, transactions, or addresses. All of this code comes complete with Solidity out of the box. The second is that it encourages standardized ways of interacting with Ethereum. These standard patterns make Solidity easier to learn and smart contracts easier to deploy. Some of the most important built-in objects and methods are shown on your screen. These include the transaction object. Here you can get things like the current gas price, as well as the address of the original account that kicked off this transaction chain. The message object. This is very useful in terms of access control and permissioning, as we shall see later in this video. Here you can get the ID of the most recent message sender, as well as the value of any crypto assets sent in this message. Addresses are the unique locations on the blockchain where external accounts and contract accounts live. You can use the built-in functions of addresses to transfer tokens, as well as call functions in contract accounts. Finally, the block object allows interaction directly with the blockchain itself. From here, you can see who mined or validated the block height, the block difficulty, and gas limit, amongst other variables. Some of these key built-ins are summarized in the table on your screen. These are very powerful, very easy objects to use. It's very, very rare indeed to see a smart contract that doesn't make use of some or all of these built-in objects. As we shall see in the very next section, they're extremely useful for implementing security, permissioning, and access control. In every software system, security and access control are of paramount significance. Bugs, hacks, and vulnerabilities cost money. However, Ethereum takes security issues to a whole new level. Here we have a system enabling transfer of cryptocurrency from contract to contract account and back again. Real value is being transferred. All of this value transfer is happening on a public ledger with information written in clear text, visible to all. And all of this is happening across tens of thousands of computers with identical copies of this ledger. There are multiple points of attack and vulnerability. The system needs to be maximally secure. The topic of security naturally requires an entire video series in its own right. Here, we will introduce some of the key features of the Solidity language that have been developed to enable best practices. There are many layers and features to security and access control, but the foundation upon which all these best practices are built are two things: function modifiers and the require statement. They're very, very often used in conjunction with the built-in objects that we just spoke about. Function modifiers are similar to decorators in Python. They're simple pieces of code that can easily be wrapped around a function. Once wrapped around a function, the code in the modifier becomes part of that function. Require statements are statements that must be true, or the function that contains them will terminate and throw an exception. With these two simple tools, modifiers and require, and with the rich set of built-in objects, it becomes much easier to implement tight security and access control. Here is a simple but practical example. This illustrates the use of all three concepts discussed. That is to say, function modifiers, the require statement, and built-in objects. This smart contract is called owner, and it has a single variable, which is the address of the owner or deployer of this contract. When the contract is first deployed, the constructor function sets this owner variable using the built-in message object. A function modifier called onlyOwner is declared in this function. It uses a require statement. This simply and clearly states that any function using this modifier has to be invoked by the contract owner and only the contract owner. Finally, this contract has a function called change price. This change price function is decorated with the onlyOwner modifier. This means that if anyone other than the owner calls this change price function, it will terminate with an exception. Thus, this provides very simple yet very effective access control and permissioning. Here is an example of a smart contract that only allows a super user to change the price. Without this modifier, anyone who knew of this change price function would be able to change this contract's price. In this video, we've introduced the Solidity programming language, a powerful high-level language, similar in syntax and structure to Java and C++. Unlike those multi-purpose languages, Solidity is specifically designed to write DeFi apps on the Ethereum blockchain. As such, it has many built-in features that aid app development. These include accounts, both externally owned and contract accounts. Solidity also features objects and variables that provide information about the blockchain state from anywhere within a smart contract. The message and transaction objects are particularly useful in this regard. On an open, distributed blockchain, security is paramount. Solidity provides some neat out-of-the-box measures to make it easy to follow best security practices. In the next video, we'll see how some of these key elements are used as we walk through a simple yet functional smart contract to represent our own cryptocurrency.